Hello, this is a video for UConn's Computer Science and Engineering 3666 course, Introduction to Computer Architecture, and you have here before you a MIPS processor. Chances are, if you're watching this video, so far in the course you've probably familiarized yourself with the MIPS assembly language, and you're just getting into the nitty-gritty of it, the hardware. So don't be alarmed if all this confuses you right now. Don't worry if this is overwhelming. First, I'd like to draw your attention right here to this familiar MIPS instruction. If you can't understand what this means, then this video might be too ahead for you. You might be watching this too early in the course. If you are familiar with what this means, you might not be familiar with what these series of ones and zeros are. This here is a MIPS instruction encoded into machine code. I have the corresponding bits color-coded with what part of the instruction it applies to. So these yellow bits here, 11001, corresponds to this T9 register right here. This 11000 corresponds to this TH register over here, both of them in green. And this pink 11000 corresponds to this TH register over here in purple. The subtract instruction, has these first 6 bits red and these last 6 bits, 100010. If you're familiar with R-type instructions, you'll recognize this white space as a shift amount. These 5 zeros here don't impact the instruction very much. I'd like to draw your attention to 4 parts of this processor over here: the instruction memory, the registers, and the data memory. Let's get a nice big circle on these. And you know what, for good measure, how about the control and this ALU as well. These are the big players in the MIPS CPU. The instruction memory is where all your instructions are stored. That's, for example, this subtract instruction right here that we're going to go step by step through. This registers block is where all your registers are stored, and this piece of hardware is also what's used to read and write the registers. This ALU, which is what does all the bulk of the math. And this block here to the right is the data memory. That's where things are stored in RAM. This is, for example, your stack pointer. Finally, up here, an important piece is the control unit. You don't need to know a lot about this to make sense of the CPU, but it's useful for making sure that the instruction can go through the CPU properly. For example, not every instruction involves writing to a register. So one of these control lines, where is it? I've covered it up a little. Reg write. Let me erase some of these circles. This control line determines whether or not the register is written to. So that's why the control is important. Anyways, what we're going to do is, using these colors, follow how this MIPS instruction goes through the CPU. I'm going to use the red, green, yellow, and purple to indicate these individual parts of the instruction, where data on the bus comes from, and this sort of teal color to indicate that it's a mixture of most of these elements. So, that being said, let's get started. By the way, just a note, each of these lines here, these are buses, meaning they carry multiple wires at one. So, our story here starts with the instruction memory. Right here, at this point, there is 32 bytes of data, and that gets split off at each one of these big dots here. We have bits 31 through 26, that represents these 4 right over here. Sorry, these 6 right over here. going to the control. And like I said before, this does some calculations, some math, some decoding to determine what bits each of these various other supporting control paths should be in order to make the instruction work right. We won't worry too much about the control right now, but it will become relevant and we will determine what some of these values are. Just know that all these blue buses here represent control. And we'll look at that later. This line right here, instruction, coming from the instruction memory, these are bits 25 through 21. That represents these green bits over here. That's the first register being read in the instruction. Likewise, bits 20 through 16 run here into register 2, the second register to be read. These pink bits, instruction 15 through 11, is what's being written to in this instruction. You can tell that from the ordering of the registers in the MIPS instruction. In different instructions, the yellow bits would actually be the ones being written to. That's why we need a control. We use a MUX for many of these controls, as you can see. And if we follow this control line, we'll see that the reg DST, short for registered destination, is what controls whether or not the yellow or the pink instruction gets written to. So reg destination would be set to 1, so our pink goes through. Oh, and one last thing. The bits 15 through 0, that includes these red bits here, these white bits here, and also these pink bits, but these red bits are all that matter. Get past here. Some irrelevant stuff happens past this juncture, but the last 6 bits of those, that's 100010, gets passed to the ALU control. These 6 bits back here determine what the ALU is supposed to do, and the ALU control down here decodes that. Alright, so that's the first step in getting this instruction to be passed. We got to follow these lines now to the ALU. So as you might expect, the bits representing T8 get passed here. This is read data 1. Now this isn't passing 11000. This is actually passing the data in register 1 or register T8. Same thing here. The data in register 9 is getting passed. Now, if we're doing a different instruction, perhaps a subtract immediate instruction, then our data might actually come from the last 15 bits. That's why we need this MUX here, the MUX for ALU source, to determine whether or not we get our second ALU inputs from read data 2 or from the last 15 bits. So these two lines come here. We obviously want the read data 2 to come here rather than the instruction bits 15 to 0. So the ALU source is set to 0. And this yellow one gets passed to the ALU. Because the ALU results is part of both the green and the yellow, the T8 and T9, I'm going to use cyan to represent it from here on forth. So you'll see that ALU result gets passed to the data memory here, and it also branches off to this MUX. We aren't working at all with data memory. We don't want to write or read any of it. And the data memory read and write is controlled by the memwrite and the memread control signals. So those both would also be set to 0. Furthermore, this line here, this control line, corresponds to mem to reg, or mem to register. We want that set to 1, so our read data gets sent through. We want that set to 0, so our ALU result gets sent through, rather than data from the memory. So we have this set to 0. Again, that's the mem to reg control. And this data follows through this line. This is the result of the contents of register T8 minus T9. And it comes back here to write data. So for data to be written to the register, the reg-write control signal has to be set to 1. So this control signal would also be 1. So that finishes the instruction, but there's one last important thing to happen in order to get the next instruction coming out of memory. And that involves all this logic up here. I'm going to draw your attention here to the program counter, which is simply a number that points to part of the instruction memory, and a variety of muxes, ALUs, and various other logic up here. That's useful in jumps and branches in order to change the next value in the program counter. But we don't need any of that for the subtract instruction. So what happens here is at the beginning of the instruction, the PC passes a value to the instruction memory to point to the line of code, but it also sends it up here to an ALU that adds 4 to the signal. Sorry, that's glitchy. That adds 4 to the value. Adding 4 will cause the next program counter value to be 4 greater, which means it'll skip 4 bytes. We skip 4 bytes rather than 1 because each instruction takes 4 bytes, 32 bits. So that said, the value of the program counter comes here, branches off here. By the way, this branch is not going to matter too much. We'll just follow this one. Our jump in our branch, by the way, is going to be set to 0. So this value is going to come up here. Again, it'll get past this ALU result, but we won't be using this. So just come here. Again, this control set to 0 comes down here. This control is also set to 0, so this goes up through here. And you can follow this back to the program counter. So the program counter gets incremented by 4, and whatever comes after the subtract instruction is sent through the ALU, and the process begins anew. That concludes this video.